welcome to the Deep Dive. Today, we're really digging in, cutting through the buzzwords. We want to get to the heart of what it really takes to build an AI system. Not just some cool demo, but something that actually lives, breathes, learns in the real world. We're focusing on bringing AI from just an idea to continuous operation. Specifically, we'll look at a powerful multimodal product review analyzer. Think of this as your shortcut to understanding the hidden complexities, the clever solutions behind modern AI, making you well-informed, fast.
That's exactly right. And what's so fascinating when you look at the sources is seeing how all these different pieces actually come together. It really highlights that AI success isn't just about one brilliant algorithm. It's about building this whole resilient ecosystem around it, which, raises a really important question. How do we actually move from those impressive lab results, those demos, to systems that are truly reliable, systems that are useful, maybe even trustworthy, and can actually stand the test of time?
Yeah, exactly. So if you're listening and wondering, where do these incredible AI advancements even come from? It's not just one lab coat somewhere, right? It seems more like a tiered ecosystem, almost like a pyramid of innovation. Understanding that structure seems key to knowing where to focus.
Precisely. When you break it down based on these technical blueprints and designs we looked at, you really see three interconnected tiers. At the very top, you've got the pioneers. These are really a small number of big industrial research labs. Google's DeepMind, OpenAI, maybe DeepSeek. They're the ones driving those fundamental architectural shifts. Things like the original transformer architecture or creating those huge paradigm-changing models like GPT or Gemini. Though an interesting trend there is a definite shift towards more closed source development, commercial pressures, competition, that sort of thing.
Okay, so the big breakthroughs happen there. What's next?
Right below them, you have a vital layer. The innovators and open source champions. Think organizations like Meta's Fair Lab, Anthropic, Mistral AI. Hugging Face is huge here too. Their role is really about democratizing AI. They take those pioneer breakthroughs and crucially translate them into tools people can actually use. They often release powerful open source models. Meta's Llama series is a prime example, or the Mistral models.
And that changes the game for developers, right?
Completely. The competitive edge isn't about having exclusive access to some secret model anymore. It shifts. Now it's about being really good at selecting the best available open models, fine-tuning them expertly, integrating them smoothly, and operationalizing them within robust systems. It's an engineering and integration challenge.
Makes sense. And the third tier?
Supporting all of this, you have the academic powerhouses. Universities like Stanford, MIT, Berkeley, Carnegie Mellon, their AI labs are crucial. They're vital for that deep foundational research, yes, but also for nurturing the talent pipeline, the next generation of AI researchers and engineers. They also do a lot of that important interdisciplinary work, robotics, HCI, AI ethics. Often, their research plants the seeds for future startups, too.
Okay, so with this whole dynamic landscape,
Yeah.
you listening, wanting to stay ahead, how do you possibly keep up? It feels like drinking from a fire hose sometimes.
It definitely can feel that way. But the sources suggest a more deliberate strategy is needed. It's not about consuming everything. One effective way is following key thought leaders, people who consistently bridge that gap between pure research and practical application. Names like Andrew Ng, Fei-Fei Li, Jan LeCun, Kastiko Zerkov often come up. They have a knack for simplifying complex stuff.
Right, finding the signal in the noise.
Yeah. Exactly. Another tactic is subscribing to those high-signal technical newsletters. TLDR AI, the Neuron, Alpha Signal, they tend to distill the really important bits. And of course, if you can, participating in major conferences, AAAI, the Data Plus AI Summit, gives you that direct pulse. It's about filtering for impact, not just volume.
Okay, let's shift gears. Imagine you've got a great idea for an AI, but it's maybe a bit vague, like we want to understand our customers better.
Yeah.
How do you actually turn that into something an AI can concretely do? That seems like the critical first step.
Oh, absolutely critical. We call it problem framing. And honestly, if you look at projects, getting this wrong at the start, well, it causes a lot of downstream pain. It's all about translating those fuzzy business goals into very concrete, measurable technical specifications, something an ML model can actually be trained to achieve.
So for our example, the product review analyzer, how did that framing work?
Right. The overarching business objective was pretty clear. Empower product teams and customer support. Give them faster, more nuanced, actionable insights directly from customer reviews. The big goals.
Yeah.
Speed up product improvements and hopefully reduce customer support costs.
Okay, makes sense. How does that become an AI task?
We framed it specifically as a multimodal classification and generation task. Multimodal because reviews aren't just text anymore, right? People upload pictures.
Ah, yeah, the images. Good point.
So we broke that down into 4 specific measurable subtasks that AI needed to handle. First, sentiment classification. Pretty standard predict overall sentiment, positive, negative, neutral, but using both the text and the image context. Second, and this one's really interesting, sarcasm detection. Outputting just a simple true-false flag.
Why sarcasm specifically? Seems tricky.
It is tricky, and it's where standard sentiment models often fail. Someone says, oh, fantastic delivery with a picture of a smashed box. You need to catch that.
Right. Okay, what else?
Third, aspect-based analysis. This goes deeper. Identify key product aspects mentioned, maybe battery life, screen quality, customer service, and extract the sentiment for each specific aspect. This gives you the why behind the overall score. The output here is structured, like a JSON object. Super useful for product teams.
That is useful.
Okay.
Number 4.
And fourth, review summarization. Generate just a concise one-sentence summary of the review's main point. This helps human reviewers quickly grasp the essence without reading everything, boosts efficiency.
Okay, so you've got sentiment, sarcasm, aspects, and summary, all from the text and image.
Exactly. And the inputs and outputs are clearly defined. Input, review texturing, user-submitted image JPEG or PNG. Output.
A structured thing with sentiment label, sarcasm flag, that aspect sentiments JSON, and the generated summary. Very specific.
That sarcasm detection using both text and image that really highlights the multimodal aspect.
It really does. It's not just keyword spotting. The model has to learn the incongruity. Positive words, negative image, probably sarcasm is that deeper understanding. Okay, problem framed. But you said it yourself, an AI is only as good as its data. And mixing text and images, getting that data ready must be, well, a whole process in itself.
Oh, absolutely. Data preparation is foundational. You can't skip this or cut corners. For multimodal data, it means meticulous cleaning, normalization, and crucially, alignment of both the text and image data. They have to make sense together for the model.
So walk us through that. What happens to the text?
For text preprocessing, it's a sequence of fairly standard steps, but you have to do them right. Lower casing everything, removing punctuation, special characters, any stray HTML tags that might creep in, removing common stop words like the is a that don't add much meaning. And then lemmatization. This reduces words to their base or dictionary form. So running, ran, runs all become run.
Why lemmatization instead of, say, stemming?
Good question. We generally prefer lemmatization because the result is usually a real word, which helps with interpretability and consolidating features. Stemming can sometimes create non-words. We might also do some optional feature engineering here, maybe flagging reviews with patterns often seen in sarcasm, like lots of exclamation points or mixed positive-negative words.
Okay, text is cleaned. What about the pictures?
Image preprocessing has its own steps. We need to standardize the images for the vision model. That means resizing them to a consistent dimension, maybe 224 by 224 pixels is common, and normalizing the pixel values, usually to a range like 0 to 1 or make it a 1 to 1.
And you mentioned augmentation.
Right. Data augmentation is crucial, especially during training. We apply random transformations, horizontal flips, small rotations, slight changes in brightness or contrast. It's like showing the model the same thing from slightly different perspectives. Makes the model more robust, less likely to overfit to just the specific training images.
Got it. So text is prepped, images are prepped. How do you bring them together, the fusion part?
This is where the data alignment and fusion strategy comes in. We use what's often called intermediate fusion or feature-level fusion. Think of it like this. The processed text goes into a specialized text encoder, like a transformer model. The processed image goes into its own specialized image encoder, maybe a CNN like DenseNet. Each encoder outputs a high-level feature representation and embedding vector summarizing its input.
So you get a text summary vector and an image summary vector.
Exactly. Then we concatenate these two embedding vectors, just stick them together end to end, creating one longer vector that contains information from both modalities.
Okay, now they're combined.
But just sticking them together isn't enough for them to interact deeply. So this concatenated vector is then fed into a subsequent, usually smaller, fusion transformer module. This module might just be 1 or 2 layers of multi-head self-attention. Its job is to let the text features and image features actually interact and influence each other.
Ah. So that's where the text saying beautiful can connect with the image showing a specific color red.
Precisely. The fusion module learns those cross-modal relationships. Beautiful red. That's the goal.
That makes so much sense. It's not just side-by-side info, it's integrated.
Exactly. Now, to handle all these reviews coming in constantly, you need a robust architecture. We use a streaming data architecture. Apache Kafka is a common choice here. Imagine your e-commerce site is a producer, sending JSON payloads review ID text image URL to a Kafka topic, say review stream.
Like a central message highway.
Perfect analogy. Kafka acts as that reliable, scalable highway. Then you have consumers' dedicated services that subscribe to this topic, pull the messages, and kick off the processing workflow for each new review.
And something has to manage that whole workflow, right? Making sure steps happen in order?
Yeah, right. That's where orchestration tools like Apache Airflow come in. We define the entire sequence of tasks consumed from Kafka, pre-process text, download and pre-process image, store results as a directed acyclic graph, or DAG, usually in Python. Airflow manages dependencies, handles retries, and schedules the pipeline. Even though data streams in, we might process it in microbatches, say every 5 minutes, using an Airflow schedule.
Can some of those steps run at the same time, like processing the text and image?
Absolutely. Airflow makes it easy to define parallel tasks. Pre-processing text and downloading pre-processing the image are independent, so they can run concurrently. That speeds things up.
Okay, and the final process data gets stored somewhere.
Yes, the final task in the DAG would typically store the prepared text and image features, maybe along with the original data and metadata, into cloud storage like Amazon S3 or Google Cloud Storage, often in an efficient format like Parquet, ready for model training or inference.
All right, data's prepped, pipeline is flowing. Let's talk about the brain itself. We hear transformers constantly. What actually is this architecture? And why was it such a revolution when it appeared back in, 2017?
The transformer architecture was genuinely game-changing. It completely shifted how we approach sequence modeling, especially for text, but its ideas have spread. Its core innovation is the self-attention mechanism. Unlike older models like RNNs that processed sequences step by step, word by word, transformers process the entire sequence at once.
How does that work? Processing it all at once?
Well, think of it conceptually like this. For every single word or token in the input sequence, the model creates 3 different vector representations: a query, what I'm looking for, a key, what I contain, and a value, the actual information I hold. Then, for a given word, its query vector is compared against every other word's key vector in the sequence. This comparison generates attention scores.
What do the scores mean?
They basically quantify how relevant each other word in the sequence is to understanding the current word. High score means high relevance. These scores are then used to create weights, essentially telling the model how much focus or attention to pay to the value vector of every other word when computing the output representation for the current word.
So, in a sentence like, the cat sat on the mat, when processing sat, it can immediately pay high attention to cat and mat.
Exactly, regardless of how far apart they are. And it does this calculation for every word simultaneously, often using multiple attention heads to capture different kinds of relationships in parallel. This ability to capture long-range dependencies instantly was a massive advantage over RNNs, which struggled with long sequences.
But it needs to know word order somehow, right, if it processes everything at once?
Good point. Yes, since the self-attention itself doesn't inherently know about position, transformers need separate positional encodings added to the input word embeddings to provide that sequence order information.
That sounds incredibly powerful. But I've heard they have a downside. Something about cost.
You're right. The original transformer architecture had a significant limitation. Its computational and memory requirements scaled quadratically with the sequence length. O-C, technically.
Meaning longer sentences get really expensive fast.
Exactly. Doubling the sequence length could quadruple the computation in memory. This made processing very long documents or high-resolution images, treated as sequences of patches, prohibitively expensive.
So how have we overcome that? Because we are using transformers for longer stuff now.
This is where some really clever recent innovations come in. One huge one is flash attention. It's fundamentally an algorithmic optimization. It doesn't change the mathematical output of the attention calculation, but it reorders how it's computed on the GPU. It cleverly avoids writing those massive intermediate attention score matrices to the GPU's slower high bandwidth memory. It keeps more in the faster on-chip SRAM.
And the result is?
Significant speedups, often 2x to 4x faster for training and inference, and it drastically reduces memory usage. Flash attention basically made it feasible to train and deploy much larger, more powerful transformer models.
Wow, okay. That's a big deal. Any other key innovations?
Another really elegant one is rotary positional embeddings, or ROP. Remember how we needed those separate positional encodings? Row P offers a more sophisticated way. It encodes the absolute position of a token by essentially rotating pairs of features in the query and key vectors by an angle that depends on the position.
Rotating features, how does that help?
It sounds abstract, but mathematically, this rotation method implicitly encodes relative positional information within the attention mechanism itself. It leads to better performance and, importantly, helps models generalize much better to sequence lengths longer than those they were explicitly trained on. It's a very clever way to handle position.
Okay, fascinating stuff. So we have this powerful optimized transformer technology. Now let's get back to our review analyzer. How do we specifically build the model to handle both text and images using these ideas, stitching those two worlds together?
Right, we architect it as a dual-encoder system with a fusion head on top. We typically build this using frameworks like PyTorch and leverage libraries like Hugging Face's transformers, which makes using pre-trained models much easier. It has three main parts working together. First, the text encoder. We need a strong language model. For this kind of task, something like DeBERTa v3 large is a great choice. It's known for handling nuances in language well, partly due to its disentangled attention mechanism. We'd load its pre-trained weights and then fine-tune it specifically on review text for sentiment, aspects, etc.
Okay, one encoder for text, then the image.
Second, the image encoder. We need something good at extracting features from pictures. A high-performance convolutional neural network, CNN, like DenseNet 121, is efficient and effective here. Again, we load weights pre-trained on a large dataset like ImageNet and then adapt it to understand product images specifically. A vision transformer, VIT, is another strong alternative nowadays.
Got it. Text encoder, image encoder. Now the critical part, making them talk.
Exactly. That's the third component, the fusion head. This implements that intermediate fusion strategy we discussed. So the review text goes through DeBERTa, outputs a text embedding vector. The product image goes through DenseNet, outputs an image embedding vector. These two vectors are then concatenated, just joined together into one longer vector.
Still separate info, just side by side?
For now. But then this concatenated vector is fed into that small fusion transformer module, maybe just one or two layers of multi-head self-attention. This module's job is crucial. It allows the text features and image features within that combined vector to interact, attend to each other, and influence the final representation.
That's the bridge, where beautiful text meets red image.
That's the bridge. The output from this fusion module then goes into a final standard classification layer, usually a simple feed-forward network with a softmax function to generate our final predictions for sentiment, sarcasm, aspects, and the summary trigger.
So it's not just running two models independently. There's this dedicated fusion step. That's really clever.
It's essential for true multimodal understanding. And when it comes to training this combined model, we don't necessarily retrain everything from scratch. That would be incredibly expensive. We use parameter-efficient fine-tuning, or PEF techniques.
How does PEF work?
The idea is to freeze most of the parameters in those large pre-trained text and image encoders. They already know a lot about language and images in general. We then focus the training effort, the gradient updates, primarily on the newly added parts, the fusion head, the final classification layer, and maybe just the very top few layers of the original encoders.
Ah, so you're only tuning a small fraction of the total parameters.
Exactly. This dramatically reduces the memory and compute needed for training, and it has another huge benefit. It helps prevent catastrophic forgetting, where fine-tuning on a specific task makes the model forget its general knowledge.
Makes sense. Keep the general knowledge, specialize the new parts.
Precisely. The actual training loop would use standard tools. A custom PyTorch dataset and beta loader to feed the paired text-image data, an appropriate loss function like cross-entropy loss, an optimizer like AtomW, and logging tools like weights and biases, or MLflow, to track experiments.
And the sarcasm detection we talked about. Is there a special rule for that?
Interestingly, no. With this kind of multimodal architecture and enough data, the model often learns to detect sarcasm implicitly. It learns that pattern of incongruity, positive language, plus a negative visual, or vice versa, as a strong signal for sarcasm, without needing an explicit sarcasm rule. It emerges from the data and the fusion process.
Wow. Okay, so you've done the hard work. You've built this sophisticated multimodal model in the lab. It understands text, images, even sarcasm. Huge achievement. But now, how do you actually get this thing working reliably out there in the real world? And maybe more importantly, how do you keep it working well over time? That seems like a whole different challenge.
It absolutely is. Moving from a model artifact to a reliable production system is where MLOps, machine learning operations, comes in. And a core part of MLOps is CI/CD. Continuous integration and continuous deployment.
CI/CD. I hear that a lot in software. How does it apply to ML?
It's the same core idea, automating the process of testing, building, and deploying code changes. But for ML, code includes not just the application code, but also the model itself, the data processing scripts, the training pipelines, everything. The goal is faster iteration, higher quality through automated testing, and reproducible, reliable deployments. It automates the path from a code commit all the way to a deployed model serving predictions.
Okay, how would you set that up? Using what tools?
A common setup uses GitHub Actions for the CI/CD pipeline orchestration. You define the workflow in a YAML file, maybe .github-workflow-cd.iml. This pipeline gets triggered automatically, say, on every push to the main branch or when a pull request is opened.
What steps does it run?
Typically, it starts with setup, checking out the code, setting up the Python environment, installing all the dependencies from requirements.txt. Then, crucial steps. Linting, using tools like Flake8 to check code style and quality, and running unit tests with PyTest to check individual functions, maybe your preprocessing logic, or the API endpoint code.
Standard software checks. What about the model itself?
Right. This is where it gets MLOps specific. A key step is model validation. An automated script runs the newly trained or updated model on a held-out test dataset data the model has never seen. It calculates key performance metrics like F1 score or accuracy for our tasks.
And what if the performance is bad?
This is critical. The pipeline is configured to fail if the new model's performance drops below a predefined threshold, say an F1 score of 0.85. This acts as a quality gate, preventing regressions from reaching production.
So the pipeline literally stops a bad model deployment. That's huge.
Absolutely essential. If all checks pass, the next stage is build and push Docker image. We use a Docker file to define the environment needed to run our model service. The pipeline builds a Docker. Image is tagged, often with the git commit hash for versioning, and then pushed to a container registry like Amazon ECR or Docker Hub.
Why Docker? What's the benefit?
Containerization with Docker packages everything needed into a single portable unit. It ensures the model runs exactly the same way on a developer's laptop, in the testing environment, and in production. Consistency is key.
Okay, image built and pushed, then deployment.
Final stage, deployment. The pipeline triggers the deployment of this new container image to the target environment, maybe a Kubernetes cluster. This often involves running commands using cloud provider CLIs or kubectl. And throughout this process, we use things like GitHub secrets to securely manage sensitive credentials, API keys, database passwords, Hugging Face tokens, infecting them as environment variables rather than hard-coding them.
Inside that Docker container, how is the model actually served?
Typically, you'd have a lightweight web framework like FastAPI running inside the container. You write Python code, maybe in src-main.py, that defines API endpoints. For example, a predict endpoint that accepts JSON input, like the review text and image URL, loads the model, runs the preprocessing and inference steps, and returns the structured predictions as JSON.
Got it. And you mentioned Kubernetes for deployment. How does that work at a high level?
Kubernetes is an orchestrator for managing containers at scale in production. It's incredibly powerful. You define your desired state using YAML files. A deployment.yaml file specifies things like which Docker image to use, how many replicas, copies of your service should run, the CPU and memory resources needed, and importantly for ML, how many GPUs each replica needs access to. It also defines health checks to monitor if the service is running correctly. Another file, service.yaml, defines how to expose your application to the network, creating a stable entry point, like a load balancer, that routes traffic to the healthy running instances, pods, of your model service.
So Kubernetes handles scaling and making sure it stays running.
Exactly. Its key benefits are scalability. It can automatically add or remove replicas based on load and resilience. It automatically replaces pods if they crash or become unresponsive. This ensures high availability for your AI service.
And I guess cloud platforms offer easier ways too.
Definitely. Managed ML platforms like AWS SageMaker, Google Vertex AI, or Azure Machine Learning Abstract away a lot of this infrastructure management. They provide streamlined ways to deploy models, often handling the containerization and scaling for you. It's a trade-off between control and convenience.
Okay, the model is live. It's containerized, orchestrated, running reliably. Huge milestone. Is that it then? Are we finally done? The system's built?
Not quite. This is where the concept of a truly living system comes in. AI models in production aren't static artifacts you deploy once and forget about. Proactive monitoring is absolutely essential. Why? Because models degrade. The real world changes, data distributions shift, and what the model learned during training might become less relevant over time.
That's model drift, right?
Yeah, exactly. Model drift is the enemy here. If you don't detect it, your model's predictive accuracy slowly, or sometimes quickly, declines, and so does its business value. You need to catch it early.
What kinds of drift are we looking for?
There are two primary types we monitor for constantly. First, data drift, sometimes called feature drift. This is when the statistical properties of the input data the model sees in production start to differ significantly from the training data.
Like people start using new slang in reviews, or image quality changes.
Perfect examples: textual drift, new terms, different phrasing; visual drift, new phone cameras, different lighting, new product types appearing in images; even population drift, the demographics of your users change. We detect this using statistical tests, things like the Kolmogorov-Smirnov test or population stability index, comparing the distributions of features in the live data stream against the distributions seen during training.
Okay, that's drift in the inputs. What's the other type?
The second type is concept drift. This one's often more subtle, but just as dangerous. Concept drift means the relationship between the input features and the thing you're trying to predict, the target variable, actually changes over time.
How could that happen with reviews?
Maybe the meaning of a 5-star review subtly shifts in your user base. Or a new product feature gets released, and suddenly what constituted good battery life previously is now considered average. The underlying concept the model learned has changed.
I see. The definition of good or bad evolves.
Precisely. We detect concept drift primarily by monitoring the model's core performance metrics, F1 score, accuracy, precision, recall on live data, where we can eventually get ground truth labels. If performance starts consistently dropping, that's a strong indicator of concept drift.
So how do you implement this monitoring?
We use specialized monitoring tools libraries like Evidently AI or deep checks are great open source options, or cloud platforms often have built-in capabilities. This monitoring process itself is often orchestrated as another Airflow DAG, running perhaps daily or weekly, comparing live data slices to training baselines or recent performance. If drift metrics cross predefined thresholds, it triggers alerts to the MLOps or data science team.
And if drift is detected, what do you do?
The response depends on the analysis. First step, investigate. Is it a genuine shift in the world, or maybe just a bug in the data pipeline? If it's genuine drift and we have access to newly labeled data reflecting the change, the most common response is to retrain the model on more recent data, possibly incorporating the new data alongside the old. If retraining isn't immediately possible, maybe we lack fresh labels, we might need to intervene differently. Perhaps temporarily disable the model for certain inputs, adjust decision thresholds, or increase the rate at which predictions are sent for human review.
This constant vigilance, this monitoring, it feels like it's the key to keeping the AI smart over time. It directly feeds into improvement, right? Like a cycle.
Exactly. That's the feedback loop. It's what transforms the AI from just a deployed model into a truly dynamic, continuously learning entity. The whole purpose of the feedback loop is to systematically leverage the system's own outputs and, importantly, user interactions with those outputs to generate new, high-quality training data. It creates that virtuous cycle that combats drift and ensures the AI delivers value long-term.
How do you architect that loop? What are the components?
There are a few key pieces you need to build. First, you need mechanisms to capture feedback, both explicit and implicit. Explicit feedback is direct user input, like a "was this summary helpful?" thumbs up down button on the UI next to the AI's output, or a way for a support agent to correct a wrongly classified sentiment. This is high-quality signal. Implicit feedback is inferred from user behavior. For example, if support agents consistently have to manually edit the AI-generated summary for a certain type of review, that implies the summary wasn't very good.
So you track how people use the AI's suggestions.
Yes. All this feedback data, the original input, the model's prediction, the user's feedback, explicit or implicit, timestamps get sent via an API to a dedicated feedback store. This might be a NoSQL database like DynamoDB or Firestore designed to handle this stream of interaction data.
Okay, feedback collected. What happens next? Does it just go straight back into training?
Not usually directly. Often there's a crucial human-in-the-loop HITL verification step. Human experts may be data annotators or senior support agents who understand the domain will review a subset of the model's predictions, especially those the model had low confidence in, or those that receive negative user feedback. They provide definitive, corrected labels. This curated, verified data forms a golden data set that's incredibly valuable for reliable retraining.
So humans clean up and confirm the feedback. Smart.
It adds a layer of quality control. Then you have an automated retraining pipeline. This is often another Airflow DAG, separate from the main inference pipeline. It runs periodically, maybe weekly or bi-weekly. It pulls the latest verified data from the feedback store, strategically combines it with the existing training data, maybe weighting the new data more heavily, and then triggers the full model fine-tuning process we discussed earlier, using PAF, etc.
And once a new model is retrained, how do you deploy it safely?
Best practice here is champion-challenger deployment. The newly retrained model, the challenger, is deployed alongside the current production model, the champion. You then route a small percentage of live traffic, say 5% or 10% to the challenger model. You monitor its performance closely in parallel with the champion on the same live traffic. If the challenger consistently proves to be better over a period, you gradually shift more traffic to it until it takes over completely and becomes the new champion.
That sounds much safer than just swapping models overnight.
Much safer. This closed-loop architecture capturing feedback, human verification, automated retraining, safe deployment is what allows the AI system's real-world usage to directly fuel its own ongoing improvement and adaptation. It keeps the system alive.
It really does sound like a living system, constantly sensing, learning, adapting, which is incredible, but also brings up some really important responsibilities, doesn't it? As these systems get so integrated and learn continuously, how do we make sure they're not just effective, but also, secure?
Fair, transparent. Building trust seems paramount.
That's absolutely critical. As AI systems become more complex and autonomous, the ethical and security dimensions become non-negotiable. We need AI security in production. And AI introduces unique vulnerabilities beyond traditional software security. Attacks can target the model itself or the data it relies on.
Beyond just securing the servers and APIs? Yes. Of course you need the basics. Strong API security, authentication, rate limiting, input validation, data privacy and access controls, encryption, role-based access, and supply chain security, vetting dependencies, scanning libraries. But then you have model-specific threats.
Like what?
One is data poisoning. This is where an adversary tries to subtly inject malicious examples into your training data, maybe through that feedback loop, hoping to corrupt the model's behavior in the future. A key defense here is anomaly detection in your data ingestion pipeline, flagging suspicious or outlier inputs for human review before they ever contaminate the training set.
Right, trying to poison the well, essentially. What else?
Another big one is adversarial attacks against the deployed model. Here, an attacker crafts tiny, often imperceptible perturbations to an input, adding carefully calculated noise to an image, changing a few words in the text that are designed to fool the model into making a wildly incorrect prediction, like making a negative review seem positive. These can even be cross-modal.
How do you defend against those? It seems hard to detect.
It is hard. One defense is adversarial training. During the model training process itself, you deliberately generate these kinds of adversarial examples and include them in the training data, essentially teaching the model to be more robust and less sensitive to such small, malicious perturbations.
Wow, okay, so you're actively training the AI to resist being tricked. That's like an immune system.
It's a bit like that, yes. It's an ongoing area of research.
Yeah.
Beyond security, there's the huge area of ethical AI in practice.
Which includes things like bias.
Exactly. Bias identification and mitigation is crucial. We need to audit our data sets, like the Amazon reviews in our example, for potential biases related to dialects, product types, user demographics, image sources. And critically, we need to segment our evaluation data to measure model performance, not just overall, but across these different subgroups. Does the model perform equally well for reviews written in different styles or about different product categories?
What if you find it doesn't perform equally well?
Then you need mitigation strategies. You might use data augmentation techniques to create more examples for underrepresented groups, or reweight the training data to give those groups more importance. There are also fairness-aware optimization algorithms you can incorporate directly into training.
And making the model less of a black box.
That's transparency and explainability. Especially for complex models like transformers, it's vital to provide insights into why a prediction was made. We integrate tools like SAA or LIME. These techniques can highlight which specific words in the review text or which regions in the product image contributed most strongly to the final sentiment classification or the generated summary. This helps users, product managers, support agents understand and trust the output, and it's invaluable for debugging when the model gets something wrong.
Seeing the reasoning builds trust.
Immensely. And underpinning all of this is data privacy and consent. following principles like data minimization, only collecting and using what's truly necessary, anonymizing personally identifiable information wherever possible, and in any real-world application using user data, obtaining clear, informed consent is essential, especially for using feedback data to retrain models. Ultimately, the organization deploying the AI system needs to take full accountability for its outputs and impacts, establishing clear governance structures and oversight. These aren't just nice to haves, they are fundamental to building responsible and trustworthy AI.
So what does this all mean? We've really covered a lot of ground today. We went from understanding where AI innovation comes from, the foundational research, all the way through the nitty-gritty of preparing multimodal data. We talked about the brilliance of transformers and the clever ways we're making them better. Then building the actual model, getting it into production reliably, using MLOps and CI/CD, and maybe most importantly, making sure it's a living system, one that constantly monitors itself, adapts, learns from feedback, all while keeping security and ethics front and center. It really is a living, breathing system. And as these AI systems become less like static tools we just use and more like these dynamic partners that learn and evolve alongside us, well, it raises a really interesting question for you listening to Ponder. How will this continuous loop, this dance between human feedback and machine learning, reshape not just how we build technology, but maybe how we approach and solve some of the most complex, evolving problems in the world together?
Yeah, and if we connect that to the bigger picture, perhaps the most profound implication of creating these truly living systems is that fundamental shift, moving away from thinking about AI as a one-time deployment towards thinking about it as a persistent, continuously adapting intelligence. Which leaves us with maybe this thought. What if the ultimate measure of intelligence isn't just what a model knows right now, but how gracefully, how effectively, and how continuously it can adapt to a future world, a changing reality that none of us have even seen yet?